The views and opinions expressed in this program are those of the speakers and do not necessarily reflect the views or positions of any entities they represent. This program is intended for educational purposes.
You're listening to
आप सुन रहे हैं
तुम सुनो था
നിങ്ങൾ കേൾക്കുന്നത്
ನೀವು ಕೇಳ್ತಾ ಇದ್ದೀರಾ
Radio Azim Premji University.
Hello and welcome to It's a Math World. We are traveling to Greece with Professor Divakaran. Hello, Professor.
Hello everyone.
It's a Math World with Divakaran and Shraddha. Episode 3. A Greek Trajectory.
Greece. Hello to Greece. Greece from hundreds of years ago. The Greece that brings to mind art, ambition, war, gods, violence, beauty, architecture, geometry, philosophy, men in long flowy robes, all at once. A civilization known for its thinkers who thought about all the mysteries of life.
Including mathematics.
Of course, mathematics. So today on this podcast, Professor Divakaran, help us understand what questions were the Greeks of that time asking? And why did these questions occur to them in the first place?
So one of the things that they were interested in was measurement, and which I think is the birth of geometry. So I think people around the world had begun measuring with some simple tools, namely a thread.
I can already feel the presence of Euclid's spirit in this studio.
Yes.
Yeah, but measurements was one of the things that fascinated Greeks.
Correct. And people were originally interested in very practical questions. Of course, once you start with practical questions, you cannot stop a curious mind. They will keep asking deeper and deeper questions, and it will eventually go into abstract questions that do not have direct relationship with everyday life.
Right.
And that's the beauty of mathematics, according to me. But the birth of these ideas is very much in the practical world.
Right.
So probably one of the things that people were interested originally were actually constructing shapes, either small objects like, say, boards or tables or something like that, or large objects like houses or temples or things like that. In either case, you need to make precise measurements, make precise shapes, triangles, circles, squares, etc. And for all of these things, you need measurement, you need geometry, you need all these ideas.
So the fundamental questions that the Greeks were asking had to do with measurements. How do we
Yes.
measure something? Do you think this also has to do with the speed at which architecture was developing in Greece?
Very likely, because the Greek architecture, whatever we know now, are fantastic.
Yeah.
They had really good measurements and really good proportions.
Yeah.
And very likely the two were related. It's very unclear whether it's like the chicken and egg, right?
Correct.
What came first?
Yeah, because they found out how to measure, they built better, bigger things. Or
Exactly.
Yeah, correct.
So
Right.
many of these things are hard to answer.
Yeah.
But it is clear that they were interested in measuring. They were interested in practical constructions. That is very clear to us.
Right.
And we have proofs of both. We
Right.
have the proof of the Greek mathematics. We have the proof of Greek architecture. And they are both phenomenal. Like with just a simple thread, we can actually do everything that can be done using a scale and compass. But the Greeks had more like stable objects like the scale and compass. And they were interested in measuring using just a scale and compass. And this is one of the primary obsessions of the Greek culture.
Right. So now, taking a step back, what did they have and what were they trying to answer?
So they were trying to ask questions like what shapes or what lengths we can construct using a scale and compass.
They had a scale and
They
they had a
a
compass.
scale and a compass.
Okay.
And now that they had these tools with them, they were interested in asking what kind of structures or what kind of shapes can we construct, including their lengths and things like that. So, for example, the truth of many of these legends are unknown, but the legend follows as so. Once what happened in Greek was that there was a severe drought. And because of the severe drought, they decided that they will go and talk to the oracle. So oracle is somebody who will answer questions.
Correct.
So it's like the god comes into the oracle, and the oracle can answer any question that you
Correct.
ask the oracle.
Correct.
So the Greeks went and asked the oracle, okay, what should we do to cure this drought? Okay, that was the question that they were interested in asking. So the oracle said, you do one thing, you create an altar which is twice the size
Of?
of the current altar. So
Okay.
they have an altar on which they pray, and this oracle said that you have to now create an altar which is double the size. So now there is various ways of understanding this question, right? One way to understand is you make the length double, and that is easy. The Greeks could easily do that, and they did that. But the drought did not stop. So then they interpreted, okay, the oracle cannot be wrong. Therefore, what we did should have been wrong. So maybe the oracle did not mean double the length, but actually double the volume of the altar or the area of the altar. Maybe that's what the oracle is asking us to do.
Right.
So the question is, can we create an altar with double the volume? So creating an altar with double the volume, assuming it's a cube, is basically same as finding cube root of 2, right? So if you multiply the sides by cube root of 2, then the volume is multiplied by 2, right?
Right.
So because the volume of a cube is side cube.
All right.
So if the original altar had size 1 and the new altar has side cube root of 2, then we will have the altar will have volume which is equal to 2, which is cube of cube root of 2.
Yeah, but which means at this point in time, they could actually calculate until this point.
Of course, they did not tell cube root of 2, right? That is still probably not there. So they just asked, maybe what the oracle is asking us to do is create an altar whose volume is 2. That's all they asked. So, of course, the idea of a cube root of 2 probably was not in their mind, but the question can exist without knowing cube root of 2.
Okay, just to clarify to our listeners, the shape of an altar is
Roughly a cube.
roughly a cube.
It's actually, I think, exactly a cube. It's like
It's a pedestal.
It's a pedestal,
Yeah.
and it's typically shaped as a cube.
As a cube.
Yes.
So the first time what they did was they just made it longer.
They made all sides double.
Double.
So you will get a altar which is volume 8 times the original volume.
Correct.
Right? But that did not work out. So they were asking, okay, what did the oracle mean? Maybe the oracle meant something else. So that was the kind of thing they couldn't even imagine that the oracle could be wrong. So that is something that they couldn't think about. So they said, okay, probably we should figure out how to interpret it correctly. The oracle only answers one sentence.
One sentence, yeah.
So now how to interpret that is up to you. You have to interpret it, understand the correct meaning, and make best of it.
And now I find myself wondering if generative AI behaved like an oracle and only answered in a single sentence and left everything to our interpretation. Wow.
So there are various such instances and stories which led people to think, what kind of numbers can you construct using a scale and compass? So this is a question that was natural to them.
So the oracle said double the size of the altar. And the Greeks thought, okay, if we increase the length of each side to twice the original length, that should do it. But it did not help. And they inferred, oh, maybe what she said was double the volume. But did the word volume exist in their vocabulary? Did they understand the concept of volume?
Yes, the area and volume was very much part of their vocabulary. They knew what area is, they knew what volume
is.
Yes,
Okay.
they knew that. Of course, many times they understood volume using some other techniques, like say, for example, water or some liquid poured into it.
Wine, not water, wine.
Right? Like, for example, how do you say that two containers have the same volume? If you can transfer the water in one jar to the water in the other jar, then they have the same volume. And if it's exactly, if the full in one jar is equal to the full in the other jar, then they have equal volume. So sometimes the understanding might be just as crude as this.
Yes.
But they certainly had the notion of volume and area both.
But now they are stuck because they don't know how to double the volume.
Exactly.
And this now spawned the question, can we measure every length that there is to measure?
So the Greeks, there are three classical problems in Greece. One is this doubling the cube, which we already discussed. Then the thing is squaring the circle. So here the question is, given a circle, can you find a square which has exactly the same area as a circle? Let's say the radius of the circle is 1 for simplicity, because it doesn't really matter. Then what's the area of the circle? It's pi. So if I want to construct a square with the exact same area, then what should be the side of that square? Root pi.
Root pi, correct, sorry.
Correct?
Yes.
So I need to construct the square with side root pi. So the question again is, can I construct a length root pi? That's the question. So this again, even squaring the circle, even though it's a question of area, it's actually a question about lengths. The earlier question about doubling the cube was actually a question about volume, but that is also a question about lengths in some sense.
Wow, okay.
Right? So these are all about what kind of lengths can you construct.
Okay, that is, what's the third one?
The third question is, given an angle, can you trisect it? So the Greek people knew how to bisect an angle, and in fact we learn it in school, how to bisect an angle.
Yes.
But they did not know how to trisect an angle, and they wanted to understand if we can trisect an angle.
And these were questions the Greeks had even before there was a standard unit of measurement.
Yes. Maybe they had some standard, but the standard might not be as standard as our SI unit.
Or even as accurate in all situations. Like
Exactly.
Because one guy would say, okay, this is the unit of measurement. Let us say this stick.
Correct.
Right? So the height of this building is going to be 2,750 sticks.
Correct.
But that's his stick.
Exactly.
Right? Someone else can have their own stick or thread or rod or box or whatever. Right? So basically everybody had their own standards at this point in time.
Correct.
There was not even a standard unit of measurement.
Correct.
But here the Greeks are saying how to trisect an angle. Right? Which seems like a very complicated problem when you don't even have a meter, centimeter, inch sorted.
So I think that is where I think the Greeks did, in some sense, beyond a point, they separated the practical and the abstract. They had the understanding that the unit did not matter. In fact, that is the whole idea of similarity and things like that.
Correct.
Right? So when I say two triangles are similar, what they are saying is, okay, this triangle has length 5 centimeter, 4 centimeter and 3 centimeter. That triangle has length 4 meters, 5 meters and 3 meters.
Correct.
What's the big deal?
What's the big
One
deal?
is centimeter, one is
A
meter.
meter.
It's the same thing. All that is matter is what is one. The moment you choose one, the difference between these two triangles, these two similar triangles, is that the one is different in these two similar triangles.
Correct.
But that's the only difference. And they had this understanding. I think part of the reason is because the Greeks lived in I think that's also part of the reason it's fascinating, right? Athens is such a small city. And it has produced so many intellectuals in such a short span of time.
Correct.
And because it's such a small city, there is nothing lost in translations.
Right.
But now we are a big world.
Yeah.
If there is no standard, it becomes difficult to talk to each other. So that's the reason why standards are more important in current day, because somebody from India will be talking to somebody from America, for instance.
Yes.
They have to understand each other.
Correct.
And probably this will also be what I'm talking today might be heard by people 100 years down the lane. I want to ensure that they also understand. So I think our need to be accessible across space and time is something that is making us more obsessed with standards.
Hi, I'm Giri.
And I'm Raghu.
So Raghu is 77 and I'm 67. And we've been following cricket like mad for the past 60 years.
I learned the English alphabet spelling Umrigar and Hazare and Mankad.
Raghu saw his first cricket match in 1955. I saw my first cricket match in 1963.
So the first test as an Indian team which we played was well before we got our independence in 1932.
Governor Raja Maharaj Singh joins thousands of eager spectators.
The whole story changed in 1961-62 tour because Nari Contractor was felled by a bumper from that dubious bowler called
Charlie Griffith.
Charlie Griffith, known as Charlie Chaka.
So Charlie Griffith has struck again.
By the time the 1980s began, the spin quartet had gone. Kapil had arrived and India had a pace attack for the first time in its cricket history.
भारत को पाकिस्तान के मुकाबले में ये पहली विजय प्राप्त हुई है. कपिल देव को मैन ऑफ द मैच चुना गया.
The inflection point is the 90s. Doordarshan would go say, can you please show this match? You now had people saying, can we host your match? The money started coming from there.
Some of the most amazing things that have happened in the last decade, which includes women's cricket, media, analytics, and the way the game has changed in this last decade.
In Well Caught by Raghu and Giri, hopefully you'll get a sense of how we must have fought and discussed and come together to write our books.
Brilliantly caught. Absolutely magnificently caught.
Well Caught by Raghu and Giri. Enjoy the show.
Coming soon, only on Radio Azim Premji University.
At this point now, they're wondering, all right, can we measure more complex lengths and more complex dimensions and more complex shapes? What answers did these questions lead to?
Yes. So, and that's really what I think the most interesting part here is. So, as I said, 1 is arbitrary. Now, the question is, once I can construct 1, which other numbers can you construct? So, immediately it is easy to, once you have 1, it's easy to construct 2, for instance. You measure 1 and then do it twice. So, you will get 2. Similarly, it's not very difficult. If you play with a scale and compass, you will be easily able to construct 1, 2, 3, 4, 5, and so on. So basically, all natural numbers are easy to construct. Now the question to ask is, can I construct 1 by 2? This again is something that we learned in school. So we learn how to bisect a side using compass and straight edge. But we can again ask, can I construct 1 by 3? This is hard. This is much harder. Can I construct 1 by 3 is a harder question, but the Greeks proved that you can construct 1 by 3 also. More generally, the Greeks proved that you can construct any 1 by n. That is 1 by 3, 1 by 4, 1 by 5, etc. All of those numbers can be constructed. Then they asked the question, okay, suppose I can construct 2 numbers, can I construct their sum? This is intuitive. Okay, this is intuitive because you take a line, measure the first distance, mark those 2 points, start from the second point, then again measure the second length from there.
Correct.
You get the sum of these 2 lengths. So that is kind of easy. So the moment we can add 2 lengths, we can also subtract 2 lengths. It's nothing much different. Can we multiply 2 lengths? That's another question that you can ask. This again is a little harder, but it is also possible using the base proportionality theorem, which said that suppose you have 2 similar triangles, then the ratio of their sides are proportional to each other. So this is the basic idea behind this.
Correct.
So this idea was used to construct similar triangles, which will help us multiply 2 numbers. So the similar triangles help us construct lengths that are product of 2 known numbers.
Right.
And this allowed us to construct, so recall that we already knew how to construct all natural numbers. We already knew how to construct all reciprocals of all natural numbers. So it was possible to construct m, it was possible to construct 1 by n. And we can construct the product of these 2, right? So you can construct m into 1 by n, which is m by n. So in other words, we can construct all rational numbers.
Right.
Using compass and straight edge.
Right.
And this is really a revelation, right? And at this point, they probably thought that, okay, this is all you can do, right? We have constructed pretty much everything that we can construct. And in fact, there were fanatics like Pythagoras who thought that these are the only numbers that existed. And And what is ironic is that it is the same Pythagoras' theorem which led to a number that is not a rational number.
Right.
And there are legends which said that the person who first openly advocated for this irrational number was executed by the Pythagoreans, which is like a strange cult with very strange beliefs and things like that.
Right.
So, of
These
course,
are mathematicians who got offended.
yes, these are mathematicians, but at the same time, they are like cults. They have like strange mystical beliefs, including things like you cannot eat beans and stuff like that.
These are mathematicians who are offended by the introduction of an irrational number.
Exactly.
I think today we are having our own Pythagorean moment when we see people who are offended by genders that are not man or woman. Very similar, I think.
They could also construct root 2. See, that's what makes it even more puzzling, right? Because root 2 came from Pythagoras' theorem. If you take a right-angled isosceles triangle with the two sides having length 1, then the hypotenuse has length square root of 1 plus 1,
Correct.
which is square root of 2.
2.
So, and that is an irrational number. They knew that, they proved that, all of that they could do.
And in fact,
But-
this might have come as a shock to Pythagoras himself,
Exactly.
who did not believe in irrational numbers.
So, his own theorem, Pythagoras' theorem, showed the existence of this number, but he was still reluctant to accept it. That is what makes it really surprising in some sense.
Okay, here I wanted to ask you, the fact that Pythagoras was reluctant to accept something that his own theorem proved. And I've also heard this against a legend that Pythagoras actually traveled to India and probably was inspired for the Pythagoras theorem by what was already proved, accepted in India by Indian mathematicians. And probably at that time, root 2 wouldn't have puzzled Indian mathematicians as much as it puzzled Pythagoras.
Possibly. So it is true that the Pythagoras theorem or versions of Pythagoras theorem existed in India. That is true. That is really true. Whether there is a connection, whether Pythagoras came to India or not, I don't know. Maybe there is, maybe he came, maybe he did not come.
Okay.
These are things that
Okay.
But it is true that Indians had, and not just Indians actually, to be honest, several cultures had independently discovered Pythagoras theorem. So in fact, Pythagoras theorem is the most fundamental aspect of geometry. Any civilization that has ever done geometry would have some version of Pythagoras theorem for them.
Correct.
It's really the backbone of geometry, right? Everything else comes from Pythagoras theorem. Even the notion of how we find distance between 2 points comes from Pythagoras theorem.
Oh God, yeah.
So it's like really, really deep. And of course, Indians did a lot of geometry. So Indians had versions of Pythagoras
Yeah,
theorem.
but Indians also got invaded and all our records were like set fire to. And I feel Pythagoras had that advantage of being in Greece and not being invaded enough for his records to be burnt. Pythagoras!
Actually, that is something that perhaps people don't appreciate enough. The Greek records were also all burnt.
Oh, were they?
In fact, the Greek records, how we know what Greek people knew is not from the Greek records, but from the Arab records. So what happened is that the Arabs, there was a particular era of the Arab culture, where Arab had the richest culture in the world. But they were mostly what they were doing at that time is, of course, they did build upon it, but the first immediate step that they did was they took knowledge from all across the world they knew, which included Greek, Europe, and India and China and all of this. They accumulated all the knowledges from everywhere and documented all of it.
And did they give credit to...
They gave complete credit to whoever.
That is so cool.
Arabs have to be really respected for that.
That is so cool.
They never said that this is our creation. They always said this is this person's creation. This is that person's creation. And they documented all of these things. And in fact, the Europe went into what is known as the Dark Age.
Right.
And during that time, any knowledge about the Greek knowledge was lost to Europeans, but later it was rediscovered
because of the Arabs.
Yes.
Oh, this is so wonderful to know. Wow.
So it's not really that of course the Greeks were brilliant. They discovered all these things,
Right.
but we would not have known that without Arabs.
So Pythagoras found out that root 2 is reality. You can't escape from it. And we can draw root 2, but probably we don't know what root 2 translates to in terms of a number, really.
Exactly. But part of the thing is this issue did not bother them so much because this representation business was not something they were so bothered
about. Yeah.
We are bothered about how to represent it in decimal or something like that.
Right.
And we cannot. Is something that we all know, right? It's a non-terminating, non-repeating decimal expansion that you get.
Correct.
When you try to write root 2. But they were not so bothered about it and they could not do it. So and that's part of the reason why there was a discomfort, right? It's a number they don't fully understand.
Right. But can measure, can draw.
Yeah, exactly.
The length of.
There is
wow.
something that makes you uncomfortable. So I do sympathize with Pythagoras in that sense.
Yeah, and it's quite amazing because now that you think of it, you cannot fully represent root 2, but ask me to draw the length very easily.
Exactly.
I just have to draw a right angle triangle where the sides are 1 and 1.
Exactly.
Wow.
So the natural question is, okay, what are all the lengths that you can construct using a compass and straight lines?
Correct.
We know that the equation of a straight line is a linear equation of the form ax plus by is equal to c. Something of that form. And the equation of a circle is something of the form x square plus y square is equal to r square. Right? R is the radius of the circle. So now what are we doing when we are finding the intersection of two lines? We are finding the common solutions to the two linear equations.
Correct.
When we are finding the intersection of two circles, we are finding the common solutions of the two quadratic equations. When we are finding the intersection of a line and a circle, we are finding the common solutions of a linear equation and a quadratic equation.
Right.
Now, I can construct a quadratic equation with these natural numbers or integers as my coefficients. So, for example, I can take the quadratic equation x square is equal to 2. And I can solve that and I get square root of 2. But now I already have square root of 2 with me. Now I can construct the equation x square is equal to square root of 2. So I will get fourth root of 2 also. Right?
Okay.
Right? That's why. Now I have fourth root 2. I have fourth root of 2 I have constructed.
Now we're getting very groovy.
Okay.
Now what if?
So I look at x square is equal to fourth root of 2. I can solve that also using the same technique. So because of that, I can construct eighth root of 2 also, and so on. So I can construct quite a bit of, it's not just square root that I can construct.
Right.
I can keep on doing one step after the other, after the other, after the other. So you can do quite a bit of it.
So I'm imagining a party where all these mathematicians have gotten together with the little pieces of whatever chalk or wood and saying, you know what, this is square root of.
Correct.
Yeah, whether you got together, what do you have today? Look at this chip of wood. Cube root of 2. Is that all you got? Eighth root of 2. Wow.
So they could always do this. But as I said, you can only solve quadratic equations. You cannot solve cubic equations. So for instance, you cannot construct cube root of 2 using compass and ruler.
Yeah, because Pythagoras' theorem had only gone as far as square root of 2.
Exactly.
So geometry was really the benchmark.
Exactly.
Yeah, so if geometry has accepted a number, then that number was mainstream.
Exactly. If you can construct a number, that's a
mainstream number.
That's a genuine number.
That's a genuine number. Oh, so the rite of passage was, can you draw that number?
Exactly. If you draw it, then it's a number. I will accept that number.
Oh. Yeah, so until not so long ago, movies were to our songs what geometry was to numbers in Greece. If a song was not in a movie, sorry, it's not playing on radio. To be a mainstream song, you better be in a movie. And to be a mainstream number, you better be in geometry.
So these questions, there were like classical problems that the Greeks wanted to answer. And they asked very fundamental questions. They were unanswered for several centuries.
Okay.
And actually, these were properly answered only recently. A question that took centuries to answer is now understandable by somebody who has 12th standard level mathematics and 1 year of hard work. What has enabled us to do this is the language of algebra. So when people say, for a lot of students, algebra is like really what, like why do we do this? So this is really why the algebra allows us to answer these age-old questions which has puzzled people for years and years and years. Not even years, actually, centuries or millennia.
Yeah, but also very frustrating if the Greeks were alive today to see for centuries we've been pondering about this and some X and Y have entered the picture and just explained everything in a flash like that. Oh, yeah. Even though the questions that the Greeks were asking then were being articulated and solved only years, centuries later, with the questions that the Greeks had and with the understanding that they had, with these two, what were the Greeks able to achieve?
So the Greeks were able to achieve a lot of things. For example, whatever could be done, they proved that it can be done. But often their difficulty is when something actually could not be done, which we now know because we have a proof that it cannot be done, they were a little stumped. They did not have a clear idea of how to show that it cannot be done.
Right. But I'm also imagining there were probably mathematicians and architects who lost their life because they couldn't explain to the king why they cannot make this building.
Yeah, probably.
What? Why can't you make this building? No, because we don't know how to measure this. And no, just chop his head off. Stupid mathematician. Because the king didn't understand why, and he could not explain why it cannot be done. Oh, sad. Sometimes it's so important to also explain why something cannot be done.
Of course, the king also has to be able to understand it. Even if you know how to explain it, the king does not understand.
Well, that's a problem that prevails even today. A lot of bosses and managers don't understand why something cannot be done in the given amount of time. And then, yeah. So, thanking Greeks for asking the right questions and thanking the Arabs for just being so cool as to acknowledging the contributions of the different civilizations, India and Greece. In our next episode, we're going to Japan. And we'll see how the Japanese found answers to their mathematical questions in the folds of paper. Stay tuned to It's a Math World.
Make sure you check out the show notes where we share the show resources and acknowledgements. And don't forget to subscribe or like our channel for future episodes.
You're listening to
आप सुन रहे हैं तो इन सुनो था
നിങ്ങൾ കേൾക്കുന്നത്
क्यों കേൾता इधर रेडियो
Radio Azim Premji University.